All right, guys, here's our mini lesson on stoichiometry. I'm going to try to keep it under 12 minutes. All right, here are the steps for doing the superstar stoichiometry method. First step, always make sure your equation's balanced. If it's not, you need to balance it. The next thing is they're going to give you some numbers for the reactants, for the products, whatever they give you, make sure it's in moles. Okay, we're going to use the BCA table. Before, change, and after is what BCA stands for, but you're only allowed to plug moles into your BCA table. So you need to use some mole island to go from grams to moles or liters to moles or whatever they give you. Once you're in moles, we're going to plug in the before boxes. Then we can fill in the change boxes. So remember, reactants are getting used up. So we do like minus 1x, minus 2x, minus 3x, depending on the stoichiometry, the balanced equation. And then products are made or produced. So we do plus 1x, plus 2x, plus 3x, or whatever the stoichiometry is. Next, we need to find the superstar, and we do that by figuring out x. So we take the moles in our before and divide it by the coefficient for each reactant. And whatever value is smallest, that is our x, that's our superstar, our limiting reactant. Okay, then we plug in that superstar's value for x, and it's all about the superstar. And we're going to solve for our after. And remember, the B box, the before plus the change equals the after. Sometimes it's minus C, right? Because sometimes we have the negatives. But plus a negative, you're going to get the same thing. Okay, and then if they want the answer in moles, you're good right there. But if they want something different, then you're going to have to convert from moles to grams or whatever they're asking for. All right, here's our first problem. If you start with 2 moles of SiO2, how many moles of SiF4 would you produce? So step 1, we got to balance this equation. Don't worry, guys, I got this one. 1, 4, 1, 2. Okay, step 2 is we have to look at what's given. And in this case, 2 moles of SiO2 is what's given. And we need to convert it to moles. Well, that's so nice, Miss Buller. This one already is in moles. So I'm going to say before we have 2 moles. Okay, and then how many moles of SiF4? So we are looking for how much is produced of this product. When they don't tell you one of the reactants, we are assuming it's in excess. A lot of times they'll say with excess HF, but if they don't mention it, assume we have excess, it's not running out, we're not worried about it. And then our products are going to always start with 0. We don't have any of these guys before we actually mix the chemicals. Okay, now we're going to do our change. So this guy gets minus 1x because of the 1, minus 4x because of the 4, and then remember our products we're making plus 1x because of the 1, plus 2x because of the 2. So now we need to find our x, and the way we do this is we're going to take our before divided by the coefficient. So for SiO2, we're going to get 2 moles divided by 1, which is just 2. And for HF, we're going to get excess moles divided by 4. Well, a lot divided by 4 is still a lot, so we still have excess. But what we're going to end up doing to find our superstar is we're going to compare those two answers. And the smaller one, oops, that's not what I want. The smaller is going to be our X, which means this chemical is our limiting or our superstar. So in this case, 2 is our x, so we're going to plug in negative 1 times 2, negative 4 times 2, 1 times 2, plus 2 times 2. Okay, so that's minus 2, minus 8 when you multiply, plus 2, plus 4 when you multiply. So now the last step is we're going to take our before, and we're going to subtract from it the change. 2 minus 2 is 0 moles of SiO2 remaining. Excess minus 8 is going to give us excess moles of HF remaining. And then 0 plus 2 gives us 2 moles of SiF4 produced. And 0 plus 4 gives us 4 moles of H2O produced. This question asks for how many moles of SiF4 would you produce, so there's my answer right there. 2 moles of SiF4 will be produced. All right, this one is very, very similar, so I want you to pause the video and try it for yourself, and then you can check your answer. All right, hopefully you got 3 moles of iron of Fe produced. So again, I balanced my equation. I filled out my before. If they don't tell me about a reactant, that's my excess. My products always start at 0. We did our minus x's and our plus x's, and here's how we solve for x down here where it says find x. We took the before divided by the 2, so 1.5, excess divided by 1 is excess, so 1.5 became my x, which means aluminum was my superstar. So we know aluminum's going to run out. That's my limiting. That's what makes it the superstar. We plug in that 1.5. The superstar's x value gets plugged in for all of these, and we solved. All right, now let's get into a more typical problem with limiting. So we're starting with 3.28 moles of AgNO3, so we have that, and 1.22 moles of Na3PO4. So we want to know what the limiting is, so that's the one that runs out first. We want to know how much of this is going to be produced, and we want to know how much is left over of the excess. Because yes, we have excess of one of these, more than we need, but we're using some of it, so there's going to be some left over that we can calculate. Hopefully this problem feels very similar. Here's kind of the differences. So step 1, I balance. That's still the same. Step 2, I plug, make sure these guys are in moles, which they are, 3.28 and 1.22. I plug those in under the chemical that they belong to for my before. So the difference is we don't have the word excess yet. And then my products, we still start at 0 and 0. The next thing we're going to do is we're going to do our change. So minus 3x, minus 1x, because those are getting used up. The 3 and the 1 came from the balanced equation. Plus 1x, plus 3x, same idea. The plus because those are getting produced. Okay. Next, we're going to find our x, and this is the part that's different. So for AgNO3, we take the before divided by the coefficient, 3.28 divided by 3, and then for Na3PO4, we take 1.22 divided by the coefficient 1 and get 1.22. So now instead of comparing a number to the word excess, we're actually comparing these numbers. The smaller one becomes our x value, so this is smaller, that's our x that we plug in, which means AgNO3 is our superstar, that's the limiting reactant that's going to run out. Okay, so we're going to plug that 1.09 in, and you can see I kind of solve these when you multiply. And then the very last step is we take the before, 3.28 minus 3.28. We get no moles of AgNO3 left over, which is the sign of the limiting. We get 1.22 minus 1.09, so we get 0.13 moles. And then we do the same for the product side. So what's our limiting reactant? AgNO3. How many moles of Ag3PO4 produced? Right here, 1.09. And how much excess remains? Well, Na3PO4 is my excess. How much is left over? We have 0.13 moles remaining after this reaction happens. All right, same problem, but now I'm adding a different thing. A student does the lab and collects 397.2 grams of Ag3PO4, and I want to know what this kid's percent yield is. So what we need to know for percent yield is probably a formula that would be helpful. So percent yield is equal to the actual yield divided by the theoretical yield. Oops, can't spell today. And we multiply that by 100 to make it a nice percent. So when I say actual yield, I'm talking about what homeboy collected in lab. Theoretical yield is the answer from stoichiometry. So when we do the BCA table, what's our answer? So in this case, let's see, we have the from the last slide, we had 1.09 moles of Ag3PO4 from the from the BCA table. So I'm going to do 1 mole, and then the molar mass is 418.56 grams. So Ag3PO4 has a molar mass of 418.56. I'm going to multiply those, and I get 456.25 grams of Ag3PO4. This is my theoretical yield. And they said homeboy did the lab and collects 397. That's the actual yield, like what you actually managed to get in the lab. So we're going to take 397.2 grams divided by 456.25 grams times 100%, and I get an 87.06% yield. that's it. If this was not enough for you, Miss Compton, who taught this class at Legend before, has a video on stoichiometry with limiting and percent yield. Just so you're aware, she does the change box a little different than us. How she finds her x is a little different, but the idea is similar enough that if you need more practice, it's there for you.